What is up, amigos? Today we have the aerodynamics of a flying chicken. So we have a chicken with a kind of a delta wing slash swept wing attached to it on top. And this comes on the heels of another video we did about a month ago maybe, of just a regular chicken flying. But then we thought, well, why limit the chicken to just what it can do naturally? Why not use the technology we have? We have the technology to make it fly better. So strapping this wing onto this chicken, we can see that there's a really cool wake. First of all, we have the wake from the chicken itself, which is a bluff body, obviously. But the wing itself is producing a very characteristic flow around a wing like this. So because it is a triangle shape, what happens is these vortices form on top. And these are these little bumps on top that you can see. So you can see like there's one bump on the left side, one bump on the right side. These are vortices that are occupying these wakes. And these wakes are effectively low pressure, which then allows the flow on top to suck down to the rest of the airfoil and produce more lift at higher angles of attack. This is called vortex lift. Now, as we go downstream, these vortices break down very quickly. So you can see just after the second plane, which is just after the trailing edge of the airfoil, you can see there's like this wandering around of this wake. These are these vortices wandering around. And as you go downstream even more and more, the vortices not only wander around, but they start to break down as well. And that's what we see in the fourth plane and in the fifth plane eventually. So this is the total subdrag plotted on these planes. And from this angle, you can see a little bit of a different view of the airfoil. So you can see like it sort of is quite thick in the middle and then it tapers out towards the wing tips. And interestingly, the vortices that it produces and just the general wake around the airfoil is very high loss, like it's quite red. Obviously, the chicken is even worse because you're producing all this drag for not much benefit in terms of the lift. I can tell you now that the lift coefficient produced by this bird with this configuration, now this modification, is 0.22. So that's like a NACA 0020 airfoil pitched at about 2.2 degree angle of attack. So it's pretty decent now. That's like a cruising kind of lift coefficient there. So now we have these exact same planes, but now it's plotting the profile drag. The profile drag is the pressure drag and a skin friction drag together, whereas the other component that we need to consider is the induced drag. If you remember the video that we just showed you with the total drag, there was a lot of red around the airfoil. Now this plot here shows that there's a lot of blue to green. So this means that most of the drag that this airfoil was producing was not actually from the profile drag. It was from the induced drag, and in particular, it should be more accurately described as vortex drag here because the vortices on top are not arguably produced from lift, so they're probably more vortex drag and induced drag together, you would say. So what we can conclude is that most of the drag produced by this bird in this configuration is actually from the induced drag and the vortex drag and not the profile drag. So this is a cool plane now. It's going straight through the middle of the bird and this airfoil, and the airfoil is acting as it should be. You can see that the flow going over it is quite sleek. It's not producing much for a wake, and it comes down at the angle. That is indicating that it's producing lift. The bird itself is not producing much lift, and it's really just a bluff body. It's like a rock just flying through the air. So the wing is really doing the majority of the lifting in this situation. So this is the exact same plane now with the total subdrag plotted. And if you remember from the total subdrag for the X planes, we saw that over the airfoil there were these two regions of very high drag, like these pockets. Well, this plane is splitting the two. That's why we don't see much of a wake on top or much of a total drag on top. And this configuration, like this area here, the bird is really producing the majority of the drag in this plane, with the wing itself producing very little drag. Now, to show you the effect of that like vortex region over the airfoil, I've put a plane a bit further out from the middle of the airfoil towards the wingtip, and this is pretty much slicing straight through that vortex region. And we can see now that the wake coming off the wing is very different to what we saw before. Obviously, the wake coming from the chicken is very small because we're not really on the chicken anymore. We're not slicing through the chicken. We're away from the chicken. But the airfoil itself is producing a very big drag, like it's a very big wake. We'll look at the drag in a second. But this is from the vortex itself. You can see it's just producing a much bigger wake than the other slice we had going straight through the middle of the airfoil. And as expected, the total drag is quite a lot in this region, even from the chicken, which technically we're not actually hitting the chicken yet. It's the flow that's going around the chicken. That is still producing quite a bit of drag as well. But the airfoil in this situation is producing a lot of drag because of that vortex. I can tell you that this entire ensemble of the chicken with the supporting structure to the airfoil and the airfoil itself produces a drag coefficient of 0.94, which is really bad. So a regular airfoil, like this airfoil by itself, would be producing a drag coefficient of maybe 0.1, with the chicken in the configuration, it goes up to 0.94. So now we have that exact same plane, but with a profile drag shown. And we can see that, as we expected from the other X-planes, that most of the drag coming from the airfoil is not really from the profile drag. It's more from the vortex drag and the induced drag, because we can see here, compared to the total drag, which showed a lot of red region, this region is showing a very orange and yellow region, and the scale is even lower. So the drag is predominantly coming from the vortex drag and the induced drag in this situation. Now we have two Z-planes, one which is going through the chicken, and then one which is just below the airfoil, like in between the airfoil and the chicken kind of region. And the wake is cool. So we have the wake coming from the chicken / supporting pole. Then we have two bluer regions, one on each wingtip. This is from the wingtip and the vortices produced here. So the airfoil does produce a wake in certain regions, but you can see over the rest of the underbody of the airfoil, the wake is quite small. So this supporting structure would probably be better if it were more streamlined. I put it really just as like a circular rod, and that's not necessarily a great thing. And the fact that we have like a triangle shape at the back indicates that it's probably the trailing edge of this airfoil, this triangular part, that is also interacting with this wake and producing a bigger wake. And as expected, the total drag is quite high here, like that wedge shape in the middle, and in the wingtip areas, they're quite high. Now the wingtip areas, I'm going to guess quite certainly that the drag coming off here is mainly due to the wingtip vortices, not due to the profile drag, although there will be a little bit because the edges are quite sharp, quite blunt on the edges, but it's predominantly going to be the vortex drag. Let's look at the profile drag to see what is happening there. And as expected, this profile drag is showing that the wakes that we were seeing from the wingtips and the drags that were produced there are not really coming from the profile drag. You can see that, okay, there is a little bit of profile drag there, but it's predominantly coming from the vortex drag, because in this plot, it's really only yellow and blue even, whereas in the total drag plot, it was at the orange and even red. We have one final wake position. We have one wake going through the chicken, but we have one wake going through the top of the vortices over the airfoil. I wanted to see what the wakes look like from here. So to confirm what we were saying with these vortices on top, we have this slice going through, and you can see that the wakes are coming from these slices. They're not coming from really the wing itself. A little bit from the leading edge, but mostly from these vortices producing these low pressure regions. And this is a increased wake. And as expected, the total drag plotted here shows that these vortices are producing a lot of drag here. So even though vortex lift is very good in terms of being able to produce lift at high angles of attack, it comes with the drag penalty, as we see here. And this is the profile drag shown here. And we can see again that, okay, there's a little bit of profile drag, but it's not the main contributor to the total drag. That's mainly coming from the vortices, which is the vortex drag in this particular case. So that's his simulation. I really enjoyed it because it was a really cool, complex situation with the vortices on top of the airfoil compared to the chicken bluff body dynamics there. So if you liked it as well, make sure to like the button there. And if you want to see more like this, click the subscribe button. And if you want to get better at CFD and or theory like this yourself, check out our courses at the link in the description. And I'll see you next podcast. Peace out, amigos.